Hey everybody, okay, we're live here returning to the Keras tutorial we've been working on. I wanted to change gears a little bit, and since we weren't getting very good results with the Jeff Bezos versus Bill Gates, I wanted to change gears and verify that we were doing everything properly with a data set where the classes were more easily discriminated between. So let's get our environment set up. I'm using Conda now on my Windows machine. I have an environment called Python 3. And let me get into the repo here. And you'll see what I've done. I've got additional notebook called Border Collie or Yellow Lab. So let's get Jupyter Notebook running. And what I did was I used that same Google image scraper to download around 600 Border Collie photos and 600 Yellow Lab photos. And just as a quick, because I'm on a GPU now, I've got a pretty nice graphics card. This is a monitoring software that I found that at least shows me what the GPU memory utilization is at, stuff like that. But yeah, I've got the GTX 1080 Ti, which is a pretty nice card. I think it's 12 gigs. So I've got the Border Collie Yellow Lab. If you're using the Python image scraper, one thing I had to do, let me see if I can get Sublime up here. I'm really used to a Mac now, so I'm a little bit clumsy on a Windows machine. Yeah, but one thing I had to do when I invoked the instance of WebDriver Firefox, not only did I have to download Firefox, which is completely reasonable, I had to download the Gecko driver for 64-bit Windows version and reference the path there. And after I did that, and I also installed Selenium via Anaconda, everything worked fine. So you may, just your mileage may vary, not sure what you're using, but I did have to change a couple of things. So let's go back to Chrome though, and I just wanted to close the loop a little bit on the Scratch convnet using just the images of Jeff Bezos and Gates. And where is that? Which one? Trying to get my best benchmark here. I don't know. We'll go back to that later. But in any event, the best I was able to get validation accuracy from Scratch was around 75-80%. Really couldn't breach that. And when you actually dive into the data in the folders, you'll see that even for the Gates class images, you end up with pictures of Bezos, Zuckerberg, other prominent people, sometimes random people. Sometimes the image is at such an angle or at such a point of view where you really can't discriminate as to whether or not it is a person. As a challenge, just look at the images in your window browser and see if they can actually be discerned by you. So that's just a good thing to remember. The machine can only learn things provided they're sufficiently discriminate between the classes. Don't think that just because it was easy to generate the training data that it actually worked. So we're going to go ahead, and you can find all the Collie photos in the repo. They should be up there. So first I'm looking in the Collie lab. I'm looking at all the different the classes there. It's going to be a Collie and a Lab. I'm just seeing how many I have. I've got 600 of Collies, 596 of Yellow Labradors. Just setting up my directory structure here. We looked at this code in another video, but really it's just to take some of the training data and put it into a validation folder for each of our labels, and we do it randomly. So that's another thing here. Where is it being randomized? Well, we're shuffling it. So for label, shuffling here. Lots of shuffling happening. So any bias which we might have created in the prior tutorials by taking the top 50 images and holding them for validation is not going to show up in this strategy. So yeah, I mean, you can a good challenge would be if you're just getting into this, and this is such a big part of creating machine learning training data, is try to write this in a more generalizable way for any number of classes. But I think this is a good kind of procedural start with a couple of sort of copy-paste elements to help you get your head around what's happening on a Windows machine. You know, the / and your Mac is going to be a little different, right? On a Mac, it's gonna look like that. But your mileage may vary there. Just Google it when you get the error. So we actually have that. So these images were already handled there. Let's invoke the generators. And just as a reminder, we're doing some basic image augmentation operations. This actually happens in memory and on the fly. So in a later video, I'll actually show you how to use this to save more images to disk. And then we can actually use those images and flow from that directory to create bottleneck features. And I think that bottleneck feature strategy, whatever you want to call it, transfer learning, fine-tuning, retraining the top layers of a network, I think it'll work better now that we have more differentiated aspects between our classes. Like a Border Collie definitely does not look like a Labrador. They have different fur characteristics, and they don't look like yellow Labradors. Typically, Border Collies are black and white, or less frequently, brown and white. They just look different. I have a Border Collie, so I know these things. So the train generator here, the validation generator, we're using test data gen. We're not applying any augmentation to that. That doesn't make any sense. So we have 1,000 images to train on, 195 to validate against, and we have the same network architecture we used last time. Just note that we have images 150 by 150 by 3 channels. If you're using Theano, the number of channels may go in front, or else you'll get a very easily correctable error through Google. One reminder, this is not a softmax classification, it's a binary classification. Had we had more than 2 categories, this would actually be the number of categories. This would be a softmax activation, and we'd be using categorical cross-entropy. Atom is a very good optimizer to use. So let's compile the model. At the compile step, if it doesn't throw any errors, then we've done a pretty good job. You've made it pretty far. A couple of notes about the new fit generator. Since the train generator is applying transformations to data, I want it to crank through batches of 32 items many times. So I want it to crank through batches of 32 items, 2,500 divided by 32 times. Maybe we could even say 2,750. I just want it to apply lots of augmentation to learn more quickly about the animals. Maybe I'll even say 3,000. It should apply lots of rotations and shifting and zooming. It's not going to flip it though. Typically, a dog is not going to be upside down in the real world. So, well, I hope maybe they will be. I don't know. But in any event, and the last thing here is the TQDM notebook callback. I'm using a better sort of output progress meter. It's called Keras TQDM. You can install it via pip. I don't think there's a conda package, but it should be fine. And what it'll do is you'll set verbose to 0, so you stop the native progress output, and we'll get a much better read on it. So let's save that, and let's get cranking. We are using a real graphics card now, so you'll see that we're cranking through this at 20 times the speed of what we were doing on my 27-inch iMac, which had, I think, an i5 Intel chip, quad core maybe, I don't know. But yeah, it's moving a lot faster. And let's actually see where we're at now. So Epic 0 is down, accuracy was 71%, validation accuracy was 86%, so that's really good. Recall with the 2 entrepreneur gentlemen, we were having trouble getting past 60-65% in the first couple of epics. So what's happening with training accuracy? It's steadily going up here. Are we getting the same with, oh yeah, so now validation accuracy is at 0.911. So even with the relatively small data set, given that the classes are fairly distinct, I think we're doing rather well. and we'll let it run for 30. My sense is going to be that it'll probably plateau. Maybe let's pull up some of these images here and actually see what's going on. Collie Lab, valid, Collie. And if I go to view, is there any easy way to see the content? Or to like preview it? Small icons, tiles. Maybe if I just open one and hit right. Yeah, so those are Collie puppies. That's a baby border collie. That's a picture of a border collie. That's definitely a collie. Another collie, 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 collie. A lot of collies there. That's kind of weird. I mean, maybe it'll pick it up. We'll actually try and predict on some of these after the model runs and see what it does. But, you know, these are all much less ambiguous than, say, Bill Gates. That's not a collie. Bill Gates or Jeff Bezos. So, I'm trying to find one that looks like mine. That actually looks like his little brother dog. But, okay, let's take a look at the lab. I did a Google search for yellow Labrador retriever. That looks like a puppy I had when I was a kid. So yeah, yellow lab, much different, much easier to discern. And when we use this data set to try to get our accuracy up even higher, I think using the bottleneck features, training on a network whose weights are tuned to predict ImageNet classes, which do focus on dog breeds to some degree, will actually do a lot better. So maybe we'll be able to take our scratch convnet accuracy and start getting that up to maybe 95% or 97% or something like that. Or maybe there'll actually be some issue endemic to our data set and we realize that maybe 5 out of 100 or 3 out of 100 are just poorly labeled, and we'll never be able to surmount that no matter how well we augment our data or what kind of sophisticated network architectures we use to train and borrow from. So I'm going to let this run. In the next video, we'll take a look at actually making some predictions, and we'll mosey on back to the idea of using pre-trained networks to speed up and improve overall accuracy. So see you then. Thanks a lot.